Good morning, chemistry students. Here are your Chapter 13, Day 1 notes. We're going to start with 13.1 Models of the Atom on your outline and finish up the quantum mechanical model. So, this is a little bit of review. Some of this information we've already talked about a little bit, but we will kind of review it or rehash it. So we're going to talk about models of the atom and the evolution of atomic models, so how our current understanding of the atomic model came to be. And so we're going to start by reminding you about John Dalton, who lived from 1766 to 1844. And remember, he had a whole atomic theory with 4 ideas, but kind of what's important there is that an element is composed of only one kind of atom and a compound is composed or made of particles that are chemical combinations of different kinds of atoms. Right, and remember again, I talked about this the other day, but atom and element, oftentimes I'm going to use those terms interchangeably, as would your textbook. Realistically, the difference between them is an element is a whole bunch of the same atoms together, while an atom, I can just be talking about 1 or 2. Okay, so they really are the same thing. They're often used interchangeably. Compounds, again, all we're saying here is a compound is different than an element because it's made of several different kinds of atoms combined together. So that was Dalton's atomic theory. We talked about J.J. Thomson. He was the person who had the plum pudding we called it the chocolate chip cookie. Model of the atom. And his idea was that electrons are evenly distributed throughout an atom that is filled uniformly with positively charged material. So remember, at that time, scientists knew about the proton, and then Thomson discovered the electron. So he got curious about how those protons and electrons were organized inside the atom. And so he thinks it looks like a chocolate chip cookie. He thinks the positively charged material, the protons, is like the cookie dough. And then the electrons that are negatively charged are like the chocolate chips, and they're pretty evenly spread throughout that positively charged material. Okay, so that was Thomson's model of the atom. Remember, it was Ernest Rutherford who was going to test it. Okay, so Ernest Rutherford, Ernest Rutherford was the person who tested Thomson's atomic theory. He used existing, supposed to be an E, ideas about the atom and proposed an atomic model in which electrons move around the nucleus like planets move around the sun. So remember, we talked about Ernest Rutherford because he conducted that gold foil experiment. So he had that gold foil. He shot those alpha particles which had positive charge at the gold foil. He had predicted that if Thomson's model was right, that those alpha particles would go straight through. But that's not what happened. He had big deflections, and then he had particles that bounced back at the source. And so he knew that the Thomson's model, the chocolate chip cookie, was wrong for an atom. So he came up, remember we kind of said Ernest Rutherford discovered the nucleus. He discovered the nucleus of an atom. And so he said, we have this positive charge all in this small area called the nucleus, and these electrons are outside of it. And he was kind of looking at the world around him and what they knew, and he's kind of looking for a way to imagine it. And he said, I think it's like planets move around the sun, right? The sun would be the nucleus of this atom. And the electrons are like these planets, okay? They're in these rings that are moving around the nucleus of an atom. Ernest Rutherford, his model explained a few simple properties but not any chemical properties of atoms. Specifically, it failed to explain why objects change color when they're heated. And this was something that most people, not even just scientists, most people were familiar with. Because, remember, we're talking about the late 1800s. This was a time when there weren't cars, and so there were blacksmiths. And blacksmiths worked with the metal. And most people would have seen a blacksmith shop and knew that the blacksmith knew when to work with the metal depending upon what color it was glowing, and that those metals would change color depending upon how hot they were. Rutherford couldn't explain why the metals did that. Okay, and so again, scientists know that they needed a better model of the atom. So again, Rutherford makes a pretty big discovery with his gold foil. He says, chocolate chip cookie, the plum pudding model, okay, that's wrong. He says, no, all the positive charge, most of the mass is in this nucleus, and we have these electrons outside of it. Okay? And he could explain some things, but he couldn't explain why some objects changed color when they were heated. So Niels Bohr lived from 1885 to 1862. He's credited with this work in 1913. And he is a young Danish physicist and a student of Rutherford. So he actually had been working with Ernest Rutherford. Okay. And he wanted Rutherford's idea. He kind of is going to build on it, and he wants to be able to explain why those objects are changing color when they're heated. Okay. So he changed Rutherford's model to include newer discoveries about how the energy of an atom changes when the atom absorbs or emits light. So he was a younger guy than Rutherford, and so he was following what other scientists were making discoveries about. And he's going to take those ideas and he's going to apply them to what Rutherford has been studying. Now, Bohr considered hydrogen. So he's going to study hydrogen because it is the simplest atom with only one electron. So Bohr decides he's going to start simple. He's going to try to explain what happens with hydrogen. Okay? So he purposely chooses the simplest atom there is. Bohr proposed that an electron is found only in specific circular paths or orbits around the nucleus. So he says, hey, I don't just find this electron anywhere around the nucleus of this atom. It's going to be in this specific circular path, which he calls an orbit. And he says that each possible orbit in the model has a fixed energy. So all he means by that is when this electron is in a specific path on one of these orbits, it has a certain amount of energy associated with it. This fixed energies an electron can have are called energy levels. So he says, again, this electron can only be found on this specific circular path, and when that electron is in that particular circular path, it has a certain amount of energy. And he says he's going to call that an energy level. Okay? Now, again, he was kind of looking to compare it to things that he knew about in the real world. So he says that these energy levels are somewhat like rungs on a ladder, with the lowest rung corresponding to the lowest energy level. So a rung is the part of the ladder that you actually step on with your feet. Okay? So we're talking again about this, about this idea of rungs on a ladder. Okay? And so he kind of compares it, because people have seen ladders, he's kind of comparing it to something people have seen. And he says that like a person can climb up or down from rung to rung, an electron can move from one energy level to another. So basically he's saying people can climb up and down on ladders. Well, electrons can move from one energy level to another. Okay? They're not necessarily just stuck in one place. He also says, okay, that like a person can't stand, so like a person can't stand between the rungs of a ladder, the electron in the atom can't exist between energy levels. So he's saying a person who's climbing a ladder can't stop in between the two rungs. The same thing is true of this electron. This electron can't stop somewhere between these energy levels. It's either in the next higher energy level or in the lower energy level. It's not somewhere in between. And like a person must move just the right distance to climb the ladder, an electron must gain or lose just the right amount of energy to move from one energy level to another. So again, he really likes this ladder idea. Again, because ladder energy levels, he sees them being very similar. He says, people, you can move up and down your ladder. Electrons can move up and down in energy levels. Just like people, you can't stop in between the rungs. An electron can't be found somewhere in between energy levels. And just like to climb a ladder, you have to be able to step that certain height to move from rung to rung, right? That's why elderly people sometimes struggle to climb a ladder, because they can't get their leg up to make that step, right? Okay, so he says just like to climb a ladder, you have to move your leg a certain distance to keep climbing. An electron has to gain a specific amount of energy to move from one energy level to another. This amount of energy is called a quantum of energy. So a quantum of energy is the amount of energy required to move an electron from one energy level to another. So he calls kind of that distance, if you will, between the rungs of the ladder, the distance between these energy levels, that distance is called a quantum of energy. And because of this, the energy of an electron is therefore said to be quantized. Which just means that an electron has a specific amount of energy. Now, he kind of keeps going with this, okay? So Bohr is really, again, like I said, he's trying to explain what happens with chemical properties and why we see things glowing different colors as they're heated, okay? So he says that the amount of energy an electron gains or loses in an atom is not always the same. So he likes this idea that energy levels are like rungs on a ladder. But what he's kind of starting to get at here is, on a ladder, all the rungs are equally spaced apart. Now, thank goodness, right? Because you're probably not looking at your feet when you climb up and down a ladder, okay? But he says, I don't think that these energy levels are all equally spaced apart, that the amount of energy between them is always exactly the same. So he says that the energy levels in an atom are not equally spaced. Specifically, the higher energy levels are closer together, so it takes less energy to move from energy level to energy level. Okay, so he likes this idea that it looks like a ladder, but his ladder's looking a little different, right? When you think of a ladder, all of the rungs are equally spaced. But if this is my nucleus of my atom, in Bohr's model, here's my first rung, here's my second rung, here's my third energy level, here's my fourth, here's my fifth, here's my sixth, here's my seventh. So those energy levels are getting closer and closer together. And this distance, okay, here between, that's what is a quantum of energy. That's the amount of energy that electron would have to gain to jump, okay, from energy level to energy level. Okay, so he likes this idea that it looks like rungs on a ladder, but he says, unlike a ladder, okay, these energy levels that an atom has, they're not equally spaced apart. They don't have the same amount of energy between them. The amount of energy between them gets less and less the further you get from the nucleus of the atom. Okay, so it's going to take less energy to move from energy level to energy level, right? The quantum of energy, this amount of energy to move right here, is really different than the amount of energy needed to move right here. Okay, so Bohr did all this work, he studied this, he publishes this, and he's done a good job, okay, because he has, when he experiments with this, he is provided with results that are in agreement with experiments using the hydrogen atom. Remember, he purposely chose hydrogen because it was the simplest atom. It only has one electron, so he only has to worry about explaining what one electron is doing inside that atom. Okay? The problem with Bohr's model, okay, is that it didn't explain the energies absorbed, because you have to absorb energy to move to a higher energy level, and emitted, because you have to emit or give off energy to jump from a higher energy level back down to a lower one, by atoms with more than one electron. So it was great that he chose hydrogen, because hydrogen was nice and easy to talk about and easy to study, and it only had one electron to worry about. But the problem is that as soon as he tried to apply his ideas to more complicated atoms that had more than one electron in them, it didn't work anymore. Okay, so again, we know that Bohr's model is wrong and that we need a better model of what's happening inside the atom. So that is going to lead to the quantum mechanical model. The scientist that's associated with the quantum mechanical model is, Erwin Schrödinger. And again, he's credited with this work in 1926. And he is an Austrian physicist. Austria, the country of Austria in Europe, not Australia, different places, okay? So, what Erwin Schrödinger did is he used theoretical calculations and experimental results and he kind of had these calculations and experimental results that were inconsistent with the Bohr model. So basically, he got different results than what the Bohr model had predicted. So he said, well, that must mean that maybe the Bohr model is wrong. So he used these calculations and results to devise and solve a mathematical equation describing the behavior of the electrons in a hydrogen atom. So he's not going to use a ladder as his model. He's a mathematician, okay? And so he says, I'm going to write an equation that describes how this electron is behaving. Now, this mathematical equation is too much for us to look at in chemistry class in high school. Excuse me. If you take physical chemistry at the college level, you'll get to do a whole lot with the Schrödinger equation. Okay? It requires calculus and such to be able to look at this. So he comes up with the quantum mechanical model, which is our modern description of the electrons in an atom as the result of mathematical solutions to the Schrödinger equation. Okay, so this is the current model of the atom. Now, it has some things in common with the Bohr model. So like okay, the Bohr model, it restricts the energy of the electron to certain values. Okay, right? The Bohr model said that, like the rung on the ladder, right? That when an electron was in a particular energy level, it had a specific amount of energy. Schrodinger's equation is going to say the same thing. Okay, this quantum mechanical model says when an electron is in a particular spot around this atom, it's going to have a certain amount of energy. Unlike, okay, the Bohr model, the quantum mechanical model does not specify an exact path the electron takes around the nucleus. Okay, so it's not like the solar system. Okay, the quantum mechanical model doesn't have a specific path or orbit that this electron is going to take around the nucleus. So how is it different? Okay, the quantum mechanical model determines the allowed energies an electron can have and how likely it is to find an electron in various locations around the nucleus of an atom. So instead of saying that there is this specific path where I'm going to find an electron going around the nucleus of an atom, the quantum mechanical model is going to say, how likely is it that I can find an electron in a particular spot around the nucleus of an atom? So one of the things that's kind of really different about the Bohr model and the quantum mechanical, the Bohr model is really pretty flat, right? You can draw the solar system on a piece of paper fairly well. But atoms aren't flat. Atoms are three-dimensional, okay? And the quantum mechanical model does a much better job of describing that. So the quantum mechanical model uses probability to describe how likely it is to find an electron in a particular location around the nucleus of an atom. So we're looking at probability, which is why we involve calculus to solve this, okay? So we're looking at how likely is it? What's the probability I'm going to find an electron somewhere in this three-dimensional space around the nucleus of an atom? So we're really looking at the probability of finding an electron within a certain volume of space surrounding the nucleus. Okay. And this space, this probability, can be represented as a fuzzy, cloud-like region. Okay, so because we're talking about probability, there's areas where we're more likely to find the electron and areas where we're less. So to give you kind of an example of cloud-like, fog is our clouds at ground level. So if you've ever driven through fog, you know that there's areas where the fog is really dense and you can't hardly see it all. And then there's areas where the fog isn't dense at all and it's easy to see. Okay? The idea here is where it's likely that you would find an electron, that fog would be really thick. It would be dense. And in this area where it's not very likely to find an electron, that fog would thin out and almost be non-existent. Okay? So this cloud is more dense where the probability of finding an electron is high, and less dense where the probability of the electron is low. And just like when you're driving through fog, there's not really specifically a border, right, where the fog starts or ends. It just kind of thins out. And then suddenly you realize, wow, I'm not in the fog anymore, okay, when you're driving. This fuzzy cloud-like region, okay, has no boundary. But it's usually limited to a probability %90 of the time. So realistically, if you've studied probability in math class, you know that actually probability never gets to zero. It just approaches zero, right? It has an asymptote of zero. It just approaches zero. It never actually gets to zero. Well, that makes it hard to imagine what these places that the electrons can occupy, we're going to end up calling them electron clouds, what these electron clouds look like, okay? So to help us be able to figure out what these electron clouds look like, we're going to say this is where we find this electron 90% of the time. 9 out of 10 times, you're going to find this electron somewhere within this three-dimensional space. one time out of 10, it's not going to be in this three-dimensional space. Okay, so typically when we're talking about the quantum mechanical model, we talk about electron clouds. So that provides us with a good spot to stop for today. Notice you don't have any homework to do tonight. So enjoy your day and have a good evening.